Come on, wake up. You know it's time for your tutoring session, right? You're not paying me to watch you sleep, you know. It's such a beautiful day out, isn't it? I had to stop myself from waking you up until the time I was scheduled for. You know, professionalism and all that. I know it must have been a really long day for you, but we really should talk about your preparations for the upcoming exam. Since it's 2 weeks from now, you'll have an opportunity to meet with me again after this, and maybe we can squeeze in another session if you feel like you need it. Why are you panicking about physics? You know I'm your calculus tutor, right? Oh, you had a physics exam today. That explains a lot. I had trouble with force diagrams at one point, so I know how difficult physics can be to grasp. You don't think you did so hot? Well, I choose to believe that you didn't. I'm at least glad I could find you in here. You weren't responding to my DMs or my calls, so I was getting worried. This library is like a labyrinth. I know the application we use for communicating isn't the best, but I think it's the best way to keep things organized without asking you to give up too much personal information. I'm just lucky I found you in the same place as last week. I feel like I'm forgetting something. Oh, right. Because of our last session, I went out to get you something. Here. Now you no longer need to borrow a calculator from your class. This will also make it easier for me eventually. No need to thank me. Really. It's an honor to work with such a brilliant student. No. Don't worry about paying for it. Consider it paid for with what you've been paying me. You've been seeing me for what? A year now? Maybe I should dub it a tutorversary gift. It wasn't that much either. I saw it on clearance because they've been phasing out that particular model of the graphing calculator. Anyway, look at me with my mouth. We haven't started talking about math at all. The second midterm is coming up in 2 weeks, so we should probably prepare accordingly. Has your professor told you what will be on the exam? Up to chapter 3, so if I remember correctly, that's basic derivatives and their applications. At this point, all material, should be relevant. So we should review just about everything. We probably don't need to discuss graphing piecewise functions and determining limits based on them. We also don't need to discuss basic limits, because at this point, you're inclined to use differentiation rules. However, we should at least discuss using the definition of the derivative to prove rules. Alright, let's warm up with proving the power rule. You don't have to do anything for me right now. Just watch, alright? At this point, we only need a loose proof for exponents greater than 0 and at the simplest level, ergo only positive integer exponents. There are two definitions of the derivative, but the most popular is the one at which h approaches 0. For a function f of x, its derivative f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. This might look familiar since you just came out of physics. A derivative is merely the rate at which a function increases or decreases. So, let's begin with proving the power rule. So, we know that the power rule seeks to use x to the power of n as f of x, and that for a function f is equal to x raised to the power of n, where n is a constant, its derivative is n times x raised to the power n minus 1. Using the definition of the derivative, f prime of x is equal to the limit as h approaches 0 of x plus h to the power of n minus x to the power of n all over h. Now, we need to somehow expand x plus h to the power of n, or find a pattern. Let's iterate the binomial expansion for a couple of positive integers. X plus h to the power of 1 is equal to x plus h. X plus h to the power of 2 is equal to x squared plus 2xh plus h squared, while x plus h to the power of 3 is equal to x cubed plus 3x squared h plus 3xh squared plus h cubed. Now, if you have played around with integers before, this is starting to look like a pattern, and this pattern is called Pascal's triangle. Pascal's triangle is formed by taking 1 and adding its adjacent integers together in each row. We start with 1 and get 1, 1, then 1, 2, 1, then 1, 3, 3, 1. Note here we add 2 and 1 together to get 3. We can continue this pattern over and over again, but this gives us the coefficients of binomial expansion with exponents. We can take a few things from this by inspection and looking at the problem overall. It all boils down to the second term of the expanded form being the most important. First, for any positive integer n, we subtract the highest degree x value, or x to the power of n, in the limit. Second, we divide the whole expanded form by an h. When we plug 0 into the expanded form, only the second term will remain, because every other term becomes 0. So, taking the triangle into account, we see that the coefficient of the second term is equal to the exponent at which the binomial was raised to the power of. We can generalize the second term as nx to the power of n minus 1 h and generalize the rest. Because we assume some kind of constant for the coefficients past the second term, I arbitrarily represent it as k here, but it really doesn't matter. Know that the coefficients do get mirrored per Pascal's triangle. Place the x to the power of n at the end and divide it all by h. We can then cancel out the x to the power of n's and rewrite the above. The next step is to cancel an h from the numerator and the denominator, and this results in something similar, right? The first term is nx to the power of n minus 1 plus all the stuff that isn't going to matter. Plug in 0 for h, and we result in the power rule that f prime x is equal to nx to the power of n minus 1. So, any questions? No? Good. Let's do another example. There's another way to prove the power rule, and that's using the alternate form of the definition of the derivative. The alternate form of the definition of the derivative takes the approach of evaluating itself as variable z approaches x. The definition defines f prime of x as the limit as z approaches x of f of z minus f of x all over z minus x. Again, this is another rate. So again, we define f of x as x to the power of n, and plugging that in gives us the limit as z approaches x of z to the power of n minus x to the power of n all over z minus x. Now, I don't know if you know this, but we can figure out a way to deconstruct z to the power of n minus x to the power of n. Just like finding the pattern for Pascal's triangle in x plus z. So, let's iterate n again. Z minus x is, of course, z minus x. Z squared minus x squared is z minus x times z plus x. Z cubed minus x cubed is equal to z minus x times z squared plus zx plus x squared. And then z to the fourth minus x to the fourth can be deconstructed into z minus x times z plus x times... What did you say? Oh, thank you for correcting my writing. Let me get the stroke eraser. Sorry about that. I really need to fix that. There we go. Anyway, these two terms are multiplied by z squared plus x squared. Multiplying that out, we get z minus x times z cubed plus z squared x plus zx squared plus x cubed. From these, we can glean a pattern of z to the n minus x to the power of n being z minus x times z to the n minus 1 plus z to the n minus 2 times x, and this reverses with z x to the n minus 2 power plus x to the n minus 1 power. Now, this combined is n terms. There are n terms for this expression, as this had 2 terms, this one had 3, and this had 4. So, replacing that in the original equation, we get the limit as z approaches x of z minus x times all of these z's and x's all over z minus x. We can then cancel out the z minus x in both the numerator and the denominator, leaving the limit as z approaches x of the z's and x's. Now, if we solve this limit, we would be setting z equal to x, and we get f prime equal to n x to the power of n minus 1. Do you happen to have any questions now? No? Alright. Please let me know if you have any questions later on, okay? Now that we're through with that, I think I need to apologize for regarding that as a warm-up. But after all this time, I'm surprised you still keep up with me. After all these lessons, I never think to plan them out to specificities like this, where I have set problems, but I may have ad-libbed all of these on the fly. They're definitely not something you expected to know out of the blue. I don't know how you do it, but good job. It's ironic that those proofs were what I introduced first, but they're technically what you're started with when they teach about the power rule. Anyway, I believe in you that you can apply the power rule with ease. Remember, f prime of x is n times x to the power of n minus 1, assuming that n is a constant and f of x is equal to x to the power of n. Alright, I think it's time we introduced, or reintroduced, some of the other rules. Let's go over them with the remaining time we have. How much time do we have again? Oh, it only took us 20 minutes. We'll be fine. Let's start with the product rule, alright? Say a function exists such that f of x is equal to g of x multiplied by h of x. This refers to two terms or two expressions being multiplied together, and they would both be dependent on x. Do you remember what the derivative of such a function is? Correct. The product rule states that the derivative of this function would be g prime of x times h of x plus g of x times h prime of x. Feel free to write it in a different way if it makes you remember it more easily. So let's start again with an example of the product rule. Let f of x equal to x squared times sine of x. If we were to take the g of x, h of x notation, we can define them as g being x squared and h being sine of x. Thus, g prime of x is 2x per the power rule. If h is sine of x, then what is h prime of x? I'll give you a hint. It's another trig function, and it starts with a cosine? Yeah. H prime of x would be cosine of x in this case. So f prime of x is g prime of x, h prime of x, plus g of x, h prime of x, which is 2x sine x plus x squared cosine of x. We can't simplify this any further, so this is the answer. Pretty straightforward, right? Yes? Alright. On to the next example. If f of x is x squared plus x inclusive times 3 tangent of x, what is f prime of x? Again, we set g of x to x squared plus x and h of x to 3 tangent x. What would be g prime of x and h prime of x? Yes, g prime of x would be 2x plus 1. And that's correct. H prime of x is 3 secant squared x. You remember the derivative of tangent x, but not the sine of x, huh? It's all coming back to you, huh? Anyway, again we write the product rule, and f prime would be equal to 2x plus 1 times 3 tangent of x plus x squared plus x times 3 secant squared x. Again, we cannot simplify this further, so this is it. Do you need to take a break before the next rule? No? Alright, let's keep going then. The next rule we should review is the quotient rule. Do you remember this one? Say f of x is g of x over h of x. Yeah, don't worry about this one. It can be a bit hard to remember. There are 3 terms to know. F prime of x would be h of x times g prime of x times h prime of x all over h of x squared. Instead of using this notation, how about we refer to the numerator as high and the denominator as low. Thus, instead of this garbled mess, we can just say low d high minus high d low all over low low. If you think of this, it might help you more than remembering the garbled mess. Feel free to think about this after, alright? Okay, let's do an example. Say f of x is 2x minus 1 over x squared plus 1. So, just like product rule, let's designate g of x as 2x you tell me what g prime of x and h prime of x are? Yes, g prime of x is 2 and h prime of x is 2x. So f prime of x is again low d high minus high d low all over low low, which is equal to x squared plus 1 times 2 minus 2x minus 1 times 2x all over x squared plus 1 squared. We cannot simplify this any further, but I'm not completely sure how much your professor likes their answers simplified. I'd accept this answer though. Here's another example. If f of x is sine of x over x, g of x is sine of x, and h of x is x. So, yeah. Very good. G prime of x is cosine of x, and h prime of x is 1. Cool thing about technology is that I can just copy and paste these strokes here, but I need to fix this a little, so if you would excuse me. There we go. Again, we replace the representations here, and we get x cosine x minus sine x all over x squared. I'm really glad you're able to pick that up so easily, even taking the initiative and telling me the derivatives of those terms before I even asked. I think you'll do just fine using this method to outline your thought process. After all, when I TA'd for your professor, I vaguely remember giving partial credit for outlining your thoughts. Yeah, I did. I worked with them for one semester. Anyway, there's another rule we need to review. This, in my opinion, is the most important rule. The rule I dread reviewing the most is chain rule. A lot of people tend to misunderstand or misconstrue this rule and often make mistakes with it. Say f of x can be rewritten to g of h of x. This means that the function containing x is within another function. The derivative f prime would be g prime of h of x times h prime of x. Note that h of x does not change inside the g prime of x. So, as an example, say f of x is the square root of 2x squared minus x inclusive. We can define two functions here such that f of x is g of h of x. Can you take a guess as to what they are? Not quite, but your H was spot on. G of x is the square root of x, while h of x is 2x squared minus x, as you said. Now for the derivatives of these. G prime of x is 1/2 x to the negative 1/2 power, because g of x can be rewritten as x to the power of 1/2. H prime of x is much simpler and is 4x minus 1. Taking f prime of x as g prime of h of x times h prime of x, the answer becomes 1/2 2x squared minus 1. I'll rewrite it down here for a better image of the answer. For the next one, I will take the chain rule example to another level and give you a threefold chain rule. Let's have f of x be sine squared of pi x minus 2. Our first function, g of x, would be x squared because sine squared is easier to explain looking like this. The entire sine function is squared here. Can you tell me what the other two functions are? Yeah, you got it. You split up sine of pi x minus 2 to get h of x as sine of x, and your third function, k of x, as pi x minus 2. You caught on very quickly. Good job. So next, Well, someone's excited, aren't they? Yes. G prime of x is 2x. H prime of x is cosine of x. And k prime of x is pi. Let's deconstruct the chain rule now for this function. If there are 3 functions, rewriting the original function, here we see that f of x is equal to g of h of k of x. When thinking about how to write the chain rule for any order of a chain like this, it's best to just think that you are only affecting the outer layer of the function for every chain. So we start with g prime of h of k of x, again leaving the inside untouched. Then we multiply that by h prime of k of x, again leaving the inside untouched. Finally, we multiply it by k prime of x. Slotting this together, we get 2 sine of pi x minus 2 times cosine of pi x minus 2 times pi. you don't need to write this one down, but there's a pretty cool thing about things like this. If you remember your trig identities, you may recognize that 2 sine x cosine x is equal to sine of 2x. Thus, f prime of x is also equal to sine of 2 times pi x minus 2 inclusive times pi. Pretty cool, huh? Honestly, sometimes I wonder why you signed on to take my lessons. You're already pretty good at this. Maybe you just need a little guidance, like we all do, don't you? But do you have any particular reason? Really? Well, that makes me very happy to hear that. Alright, let's move on to the next and final topic. I am getting a bit tired. What did I do today? Nothing much. Anyway, based on your understanding in the last session, I don't think I need to review implicit differentiation with you. But just in case, let's review it one last time. Alright, so a few notes first. I think I'll close it out for this session, so I won't ask for your participation from here on out. I'm sure you know some of these already. You begin by applying both sides of the equation you're given with dx. Often for these problems, it is best to have a mindset containing the chain rule and product rules. Little fun thing here. If you have a regular equation, y equal to f of x, that is, the right is only dependent on x and only has x as a variable, and you apply dx to both sides. On your left, you just get dy dx as your derivative. I like to call this explicit differentiation as opposed to implicit differentiation, where you're trying to get y from an equation where y is not explicitly defined. Going back to an example here, let's say 2xy plus y squared is equal to x plus y. Find dy dx. The first thing is to apply dx to both sides as said before. Here we can apply d dx to every term on both sides. The first term, 2xy, uses the product rule and becomes 2 times d dx xy plus dy dx x inclusive. The next term, d dx y squared, can be thought of using the chain rule. This becomes 2y dy dx. Because we do not know what y is, but it's dependent on x in this case, so we can write it as dy dx. The right side is pretty straightforward, as the dx dx's cancel to ones. Simplifying this further, we get 2y plus dy dx, 2x plus 2y dy dx equaling to 1 plus dy dx. Now the last step is to isolate dy dx, and the first step in doing that is getting all dy dx's to one side as such. I subtracted dy dx from the right to the left and subtracted 2y from the left to the right to result in the following. We can then divide the 2x plus 2y minus one term to the other side to obtain this rational function as our derivative. Do you have any questions before I pack my things? No? Alright. Very good work today. You did very, very well. Are you headed out too? You're gonna stay a while. I hope you don't sleep too long in here. I think the library closes in a few hours. I think it's time I headed out then, for us to go our separate ways then. Good work again. What's this? A piece of paper. A phone number. Your phone number. Maybe you're right. Yeah. Maybe it would be best if we did this instead. Thank you. I'll see you later. Text you for the next session, right? Alright, if you insist.